we present WordRobe, a novel method for generating 3D garments with textures via text prompts. WordRobe is capable of generating 3D garments with high-quality textures via simplistic text prompts. Unlike existing text to 3D optimization-based methods, WordRobe performs single feed-forward generation, which is optimization-free, drastically reducing the generation time. The generated 3D garments are canonical or unposed. That is, they can be easily adopted in standard graphics pipeline, such as cloth simulation or animation. WordRobe offers a flexible and intuitive way to create high-quality 3D garments. An end user can easily describe the garment's geometry, as well as appearance in natural language, to enable fast design prototyping. We will now describe our methodology in detail. Given a text prompt, for example, a blue denim jacket with hood, we pass it to the text encoder of clip to obtain a clip embedding psi. This clip embedding is then passed to an MLP in order to map it to a suitable latent garment code phi, a vector defined on an already learned 3D garment latent space, omega. The garment latent code, phi, is then passed through a two-step coarse-to-fine decoding process to obtain an unsigned distance field representation of the garment geometry. The garment mesh is obtained by running a variant of Marching Cube's algorithm, modified to handle UDF representation. In order to learn a rich latent space of 3D garments, we employ a two-stage encoder-decoder architecture. The choice of the encoder is DGCNN, which takes points sampled on a garment mesh and encodes them into a garment latent code, phi. This phi is then decoded by the MLP decoder D-course into a coarse UDF representation, sigma coarse. In the fine stage, phi is passed to the MLP decoder D-fine, which predicts residual UDF sigma delta over the coarse UDF. Finally, sigma delta is added to sigma coarse to obtain sigma fine, the final garment UDF. For computing UDF losses for backpropagation, we take ground truth garment mesh G and pass it to mesh UDF to obtain ground truth sigma fine. For coarse UDF, we take the original mesh, apply decimation and Laplacian smoothing, and pass it to mesh UDF to obtain ground truth sigma coarse. We also employ a latent loss, which encourages the garment latent space omega to be more organized and disentangled. Please refer to the main paper for details about the loss functions. The learned latent space omega supports garment interpolation for providing more command over the generation. For example, given latent codes phi 1 and phi 2 of two garments, a weighted average can be taken to get another meaningful latent vector, phi average, which when decoded results in another garment between the two. The mapping network MLP map plays a major role in mapping the clip embedding space to the learned garment latent space, enabling text-based garment generation by predicting garment latent code from the corresponding clip embedding. However, in order to train the mapping network, a large number of distinct garments with their latent codes and reasonable text descriptions are required. To avoid explicit text annotations, we propose an automated data generation and weekly supervised training strategy for training the mapping network. We start with the garments from the dataset, render them from arbitrary viewpoints to obtain depth maps, and feed them to depth condition control net to generate diverse garment images guided by a template text prompt. The generated garment images are then given to the clip's image encoder to obtain corresponding clip embeddings. Simultaneously, we sample points on the garment surface and pass them to the trained garment encoder to obtain corresponding latent codes, which belong to the garment latent space omega. This strategy gives us paired training data, that is, clip embeddings and corresponding garment latent codes, required for training the mapping network. Once trained, the mapping network learns to map the clip embedding, coming from clip's text encoder to the garment space. Once the 3D garment mesh is generated, we perform UV parameterization using an off-the-shelf parameterization method, OptCuts, to obtain a UV map. The next task is to generate and impart textures onto the UV space, driven by the input text prompt. To achieve this, we first perform orthographic projection of the 3D garment mesh from the front and back views to obtain depth maps and composite them into a single image, producing a view composited depth map, pi depth. Pi depth is then passed to a depth condition control net, which synthesizes a view composited RGB image, pi RGB, guided by the clip embedding psi of the input text prompt. Finally, the textures from pi RGB are projected onto the UV texture map to obtain a textured 3D garment mesh. While generating multi-view images from text using latent diffusion model-based control net, conditioned on depth or anything, results in inconsistency across views, even if the random seed is same for all the views. Therefore, existing texture synthesis method or text-to-3D methods rely on optimization-based strategy to achieve view consistency up to some extent. We discover a useful property of control net, that is, when all the views are composited in the same image, the resultant generation is highly consistent across views in terms of colors, lighting, etc. We found this as empirically true for any object in general. We argue that in case of garment, front and back depth map views are sufficient to obtain view-consistent texture image. We now show the qualitative results of our method. WordRobe can generate a wide variety of 3D garments with arbitrarily diverse textures. We now show the qualitative results from text-guided texture synthesis pipeline of our methodology. We now show the qualitative comparison of our method to existing SOTA text-to-3D methods. We show a qualitative comparison of the geometry of our garment generation method with DrapeNet in terms of learning and decoding the garment latent codes. Following visualization highlights the ablation study over the choice of loss functions and isolated noise in the single decoder variant of our proposed method, which essentially justifies the need of two-stage decoding strategy. Though we aim to generate 3D garments from simplistic user-friendly text prompts, our framework is capable of handling complex and detailed prompts very well. We can also compose different garments generated via WordRobe to create complex clothing styles. Please refer to supplementary draft for more details. First, demonstrate the interpolation capability of our method by interpolating latent codes to generate interpolated 3D garments. For each row, the first column is the source garment, the last column is the target garment, and in between columns contain the linearly interpolated 3D garments. WordRobe offers text-based latent manipulation to allow editing of garment features. WordRobe supports Sketch or Scribble-based 3D garment generation and editing to allow a more descriptive and controllable way for garment creation. Sketch can be used to describe the geometry of the garment, while text can be used to describe the appearance or color. We can observe that WordRobe adheres well to the geometry described within the input sketch. WordRobe can also extract 3D garments from in-the-wild reference images. being unposed or canonical. Garments generated using WordRobe can be easily integrated in standard simulation or animation pipelines. Thanks for watching.